Ever wondered how scientists separate mixtures in the lab? One of the most common techniques is thin layer chromatography, or TLC for short. This ingenious method is a workhorse in the world of chemistry, playing a vital role in everything from pharmaceutical research to food safety testing. It's a world that's as fascinating as it is complex, and we're about to explore it together. Ready to dive into the world of TLC? Buckle up, because here we go. Alright, first things first, the principle of thin layer chromatography, or TLC for short. Imagine a race, where each runner has a different speed and endurance. Now, replace the runners with compounds and you have TLC. Here, the racetrack is the stationary phase, typically a thin layer of adsorbent material spread on a flat inert substrate. The runners, or the compounds, are carried forward by the mobile phase, which is a suitable liquid solvent. Now, every compound has a different affinity for the stationary phase and the mobile phase. This difference in affinity causes the compounds to travel at different rates, thereby leading to their separation. This separation is based on the relative amounts of each compound distributed between the stationary phase and the mobile phase. That, in a nutshell, is the principle of TLC. But what about the materials used in this process? The next big thing in thin layer chromatography, or TLC, is the adsorbents. These are not mere spectators in the process, but active participants that are pivotal in the separation of compounds. But what exactly are adsorbents? Picture them as the silent heroes of TLC, the stationary phase where the magic of separation occurs. There are several types of adsorbents used in TLC, each with its unique properties. The most commonly used include silica gel, alumina, and cellulose. Silica gel, for instance, is popular due to its high polarity, making it ideal for separating polar compounds. Alumina, on the other hand, is less polar than silica gel and is often used for the separation of non-polar compounds. Cellulose, a versatile one, can separate a wide range of compounds due to its ability to form multiple types of interactions. Now let's delve into the activity of these adsorbents. You see, the activity of an adsorbent is influenced by its polarity, particle size, and pore size, which all contribute to its interaction with the compounds. The stronger the interaction between the adsorbent and the compound, the slower the compound moves, and vice versa. This is what allows for the separation of compounds in TLC. For instance, a highly polar compound will have a strong interaction with a polar adsorbent like silica gel, causing it to move slowly during the chromatography process. Conversely, a non-polar compound will have a weak interaction with the same adsorbent, causing it to move faster. This difference in movement is what allows us to separate and identify the compounds present in a mixture. So the choice of adsorbent plays a key role in TLC. It's not just about picking any adsorbent, but selecting the right one that will provide the optimal separation for the compounds you're working with. Now, how do we prepare a TLC plate? But that's a story for another scene. Stay tuned. Time to get our hands dirty. Let's prepare a TLC plate. First, we need to choose our plate material. Glass or aluminum are common choices, but make sure it's coated with a thin layer of silica gel or alumina, our adsorbent. This thin layer is where the magic of separation happens. Next, we draw a pencil line about 1.5 centimeters from the bottom of the plate. This is our baseline. It's crucial not to use ink or marker for this line, as they could interfere with the results. Then we apply our sample on this baseline using a capillary tube. We need to deposit it as a small spot, and it's important to keep the spot above the level of the developing solvent we'll use later. Now we're ready to introduce our TLC plate into a developing chamber, often a simple glass jar. But let's not forget to add a piece of filter paper soaked in solvent to the chamber. This ensures a saturated atmosphere, promoting even development of spots. Finally, we carefully place our TLC plate in the chamber, ensuring the baseline doesn't touch the solvent. The solvent will rise up the plate by capillary action, carrying our samples along with it. And voila, we have our TLC plate ready. What's next? Now, the real action begins, the development of TLC. We're going to dive into the heart of thin layer chromatography, where the magic really happens. The development process starts with the TLC plate, which we previously prepared with an adsorbent and our sample. This plate is then placed in a developing chamber, a sealed environment containing a small volume of solvent, or what we call the developing solvent. The solvent level in the chamber is below the line of the sample application. This is crucial because we don't want our sample to dissolve into the solvent. We want it to stay on the plate, ready for the ride of its life. When the TLC plate is placed in the solvent begins to ascend the plate by capillary action. As it moves upwards, it encounters the sample. Here's where the fun begins. Each component in the sample interacts differently with the adsorbent and the solvent. Some components stick to the adsorbent, while others prefer to go with the flow of the solvent. This creates a beautiful dance of separation. Components that interact more strongly with the solvent move up the plate faster than those that interact more with the adsorbent. This process, the differential movement of the components, is what creates the separation. The rate at which the components move is influenced by a few factors: the nature of the adsorbent, the type of solvent used, the temperature, and the specific interactions between the sample and these elements all play a role in the dance of separation. Once the solvent has almost reached the top of the plate, we remove the plate from the chamber. The solvent front is marked, and the plate is allowed to dry. Once dried, the different components appear as spots on the plate. The position of these spots gives us valuable information about the sample, but that's a story for the next scene. That's how TLC development happens. But how do we evaluate the results? Stay tuned as we delve into the evaluation process and learn how to read the story that the spots on our TLC plate are telling us. The moment of truth, evaluating the TLC. Evaluating the results of a TLC experiment is a science in itself. It's all about interpretation and understanding. The process begins with visualization. After the developing solvent has run its course up the TLC plate, we examine the plate under ultraviolet light or iodine vapors. This reveals the different compounds as spots on the plate, each representing a different substance. But it's not just about spotting the spots, it's about understanding what these spots mean. This is where the RF value comes in. The retention factor, or RF, is a calculated number that helps us identify each substance. It is the ratio of the distance traveled by the substance to the distance traveled by the solvent. So take a ruler, measure these distances carefully, and calculate the RF value. This unique number is like a fingerprint, helping us identify the substance. The lower the RF value, the less distance it has traveled, indicating a more polar substance. Conversely, a higher RF value means the substance is less polar. But remember, RF values are not absolute. They can vary depending on the solvent used or the temperature. So always compare your results with a reference or under controlled conditions. Evaluation gives us the results we need. But where do we use TLC? TLC is not just a lab technique, it has a wide range of applications. Let's delve into a few, shall we? In the pharmaceutical industry, TLC is used to identify and quantify drugs and their metabolites. It helps ensure product integrity and safety, crucial in a field where precision is vital. Moving over to the food industry, it plays a key role in detecting food adulteration. It helps identify harmful substances or unexpected ingredients, ensuring the quality and safety of our daily meals. In the realm of forensic science, investigators use TLC to solve crimes. It's instrumental in identifying substances found at crime scenes, be it drugs, explosives, or inks from a suspicious note. In environmental science, it aids in monitoring pollution levels by identifying and quantifying pollutants in air and water samples. So that's why TLC is such a big deal in chemistry. Fascinating, isn't it? Well, that's a wrap on thin layer chromatography. We've journeyed through its principles, explored the role of adsorbents and their activity, delved into TLC plate preparation, and traced the development of TLC. We've also evaluated TLC, shedding light on its importance in scientific research. Lastly, we've looked at its various applications, underscoring its versatility and value. That's quite a bit to take in, isn't it? But don't worry, we'll be here to guide you through it all. Thanks for watching. Subscribe for more because you won't find me later.